Hello, it's Lewis here from GCSE and A-Level Physics Online, and I have this video here which covers the entirety of the AQA GCSE Physics course. So I've gone through all of the topics that you need to understand for GCSE Physics. I explain them clearly, I show the equations that you should remember, the units that you're using, as well as actually explaining what's happening in terms of the physics, hopefully in an interesting manner. I've also got the required practicals that you need to know about. Now, a lot of these you will have done in school, but it's always good to remind yourself before you go into any exam about all of the kind of required practicals, the kind of skills that you've gained during the last couple of years. Now, I've covered everything that you need to know for the AQA GCSE Physics course, but some people might be doing the AQA Combined Trilogy, the double science. Now, there's extra information that you might not need to know. So anything which is for the GCSE Physics only, I've often written in blue pen, and there's also the word here at the top where it says Physics. That is for the Physics only, not the Combined Double Award. Now, everything in this video is suitable for the higher tier paper, but a lot of you watching this video might be doing the foundation tier exams this summer. So what you can then do is if you go to gcsephysicsonline.com, you go to the AQA page, you'll find that then there's some student guides which you can download for free. Now, in these guides, which I've written for you, you basically can tick off all material as you cover it in this video, and that will help with that final bit of revision. It also makes clear then which material is for the foundation tier, which is pretty much everything that's in normal text, the stuff for the higher tier paper, which is in bold, and anything which is for the GCSE Physics exam only, not the Trilogy, and that's highlighted with this blue colour by the side. You can also find on my website hundreds and hundreds more videos that help you with everything you need for physics. There's worked examples, there's the mathematical skills, there's extra tips about exam revision and so on. So please do spend a bit of time having a look at gcsephysicsonline.com. Until then, I really hope this video is useful for you as you go into your final stages of revision before your exams this summer. Thank you for watching. Now, energy is a bit like money, and it can be stored in different places or maybe transferred from one store to the other. And we can also think of it a bit like a liquid that's maybe transferred from different store to different store. Now, there are a number of different stores that we need to consider. So we have kinetic energy, which is due to how quickly things are moving. We've got elastic potential if you maybe deform an object, like you squash it or squeeze it. Gravitational potential is to do with how high you move something. And then we've got thermal, which is the internal energy store, as well as a few others. Now, what we can do is, with energy, we can actually work things out. And if we wanted to work out the kinetic energy, for example, the kinetic energy is equal to a half mv squared, where the v here stands for the speed of the object, and that's measured in meters per second. We should always measure our mass in kilograms, and then this means that the unit for energy is the joule. This energy is equal to a half ke squared, where e is the extension of that object, not how long it is completely, but how much longer it has become. And again, what we do, we measure our extension in meters. K is the spring stiffness, and this is measured in newtons per metre, and once again we measure our energy in joules. Our gravitational potential energy, EP, is equal to mgh. So here again we have our energy in joules, our mass in kilograms. H is the height that something's moved through in metres, and G is what we call the gravitational field strength. And on Earth this has a value of 9.8 newtons per kilogram, but this does depend on where you are in the universe. Some things like the moon, for example, have a much smaller value of their gravitational field strength. When it comes to looking at thermal energy, what we can do is we can change the thermal energy of something by looking at mc delta theta. So here what we have is our theta, that's our temperature, and that's measured in degrees Celsius. We measure our mass in kilograms, and this thing down here, little c, is our specific heat capacity. And this is the amount of energy required to raise the temperature of 1 kilogram of something, of the substance, by 1 degree Celsius. So that means the unit for this are joules per kilogram per degree Celsius. So we have these different stores of energy, but what we can now consider is the different ways that energy is transferred from one store to the other. And there are 4 main transfers that we need to think about. So these are our 4 transfer processes. You've got heating, electrical working, radiation, and this could be things like sound waves, or it could be light waves, and also the rest of the parts of the electromagnetic spectrum. And finally, we have mechanical. Now, where it's really important to look at the way that energy is transferred from one store to the other. And what we might consider is at the start of a process, we can maybe consider the energy store. We then need to define a clear end point, and we can consider how the energy is stored at this point. And what we can then do is think about the transfer as well. So these are some of the things we need to think about. If you've got an object projected upwards, maybe it starts as the kinetic energy store and ends up transferred to the gravitational potential store. If you've got a moving object hitting an obstacle, it might end up going from the kinetic store, radiated by sound perhaps, into the thermal store of the surroundings. If you've got something which is accelerating, depending on what provides this force, you might then increase the kinetic energy store. You've got to be familiar with all of these and get used to doing different problems where you might have different energy stores, and that just comes with practice. It's also worth considering how quickly that transfer takes place. And what we can then think about is the idea of power. So power is defined as the rate at which energy is transferred or at which work is done. Now we can say that power is equal to the energy transferred divided by time, and the word rate just means the amount per second. Or we can also look at power as the work done per unit time. And we always measure energy and work done in joules. If we measure time in seconds, this then gives us a power measured in the watt. Now when we think about an energy transfer process, although some of the energy might be transferred to a useful store at the end, some of the energy might also be wasted. Perhaps it's going to heat up the surroundings. And what we can then think about is something called efficiency. And efficiency is often given a number between 0 and 1, or between 0 and 100%. And we can work out the efficiency by looking at the useful output energy transfer divided by the total input energy transfer. Effectively, the more energy that's transferred usefully, the higher the efficiency. And we can do the same thing where we're maybe not thinking about the energy transfer, but the power, and we can look at the useful power output compared to the total power input. And finally, we can think about energy resources. And what we're talking here is about things that are maybe used for transport, for example, cars. We might think about electrical or electricity generation. And finally, we can also use these for heating our homes and businesses. And what we then need to do is think about maybe different ways in which we can generate electricity. There are two main categories. We've got non-renewable and renewable. Non-renewable resources, once they're used up, we can't replenish them. So we're thinking about coal, oil and gas, as well as nuclear fuels. And when we talk about nuclear fuel, we're often thinking about uranium or plutonium. When it comes to renewable energy resources, so we have biofuel which can be burnt, and the reason that we burn all of these or use this to generate heat is to boil water. Water turns a turbine which then turns a generator which generates electricity. One way we can get away with not burning things is to use wind turbines, where it's the power of the wind directly which is causing the generator in the top of this to turn. We can use solar cells which turn that sunlight into electricity. We also have geothermal, hydro, wave and tidal, where these are just different ways of having moving water hitting a turbine blade to cause a generator to turn. So that is energy for AQA. So this video is a summary of the AQA electricity topic. And what we have in electrical circuits are a load of small electrical components. And what we need to do is we need to draw out circuits, and to help us with this, we have some circuit symbols. So some of these might be common from before, but there's a few extra ones, things like light-dependent resistors, diodes, and so on, that it's worth just spending the time memorising what all of these stand for. And the reason for this is it allows us to draw circuits really simply. Now, in the simplest case, we might have a power supply, so a cell. We might have an ammeter, and you always put the ammeter in series. And this is connected to maybe a lamp. And when the circuit is connected, it starts shining. We can also use a voltmeter to measure the potential difference across a component. So it's always worth remembering that ammeters go in series and voltmeters go in parallel. So what we have here is our really, really simple circuit. Now for this one here, what we can think about is the rate of flow of charged particles around the circuit. That's what is transferring the energy from the cell, in this case, to the lamp. And we've got to remember that electric current is the rate of flow of electric charge. Now, one of the equations we can use is that Q is equal to I times T. Now, somewhat confusingly, we use Q as a symbol for charge, and charge is measured in coulombs. We use I for the current. This is like the intensity of current, and we measure the current in the unit of the amp, and then time we measure in seconds. And really what electric current is the flow of electric charge, and in a circuit like this where we have maybe a DC supply, so it's a direct current, we've got the flow of electrons in the wires. Now we can also think of this electric current which is going through a component. It depends upon the potential difference across it, V, and also the resistance of that component. Effectively, we're going to have a bigger current flowing if you've got a bigger potential difference, but if you have a bigger resistance, that reduces the current. And what we have here is V stands for our potential difference, and this is measured in volts. R is the resistance measured in ohms, and then once again the current is measured in amps. Sometimes a more useful equation is V equals I times R, and you can apply this to any part of the circuit. If you know the potential difference and the resistance, you can then work out the current that is flowing. But when it comes to resistance, we need to look at the resistance of certain components. And we can set up a simple circuit a bit like this, and what we have is a power supply, we have a variable resistor, and this then allows us to change the current and the potential difference across a component. And we can do this for the following things. And we need to look at the characteristics of resistors, lamps, and diodes. Now, if we have a resistor, what we find is when we plot values of current and potential difference, we get a straight line that goes through the origin. And what this means is that as you have a greater potential difference, you've got a greater current that flows, and that's because the resistance is constant. In actual fact, this is a great example of something called an ohmic conductor. And provided this stays at the same temperature, the current is going to be proportional to the potential difference. If, however, you have a filament lamp, this isn't an ohmic conductor, and what we find is we get a graph that looks a bit like this. What that means is, as this gets hotter and hotter and gives out more light, the resistance increases. So this one here, you've got a changing resistance for this light bulb. If you have a diode, on the other hand, the whole point in a diode is it works a bit like a one-way valve, and it only lets the current flow in one direction, so we get a graph like this. Effectively, if you've got a negative potential difference, the value of current is 0, but when you have a high potential difference, loads of current can flow through, and this really allows us to control the way that current flows in a circuit. Now, there are two other components that we can investigate. One of them is a light-dependent resistor, and if we look at the resistance and the amount of light intensity, with an LDR, when we increase the light intensity, the resistance decreases. And the same kind of thing happens when we have a thermistor. So a thermistor is a thermal resistor. Once again, if we have the resistance on this axis of the graph and we look at the temperature on this axis, as we heat this up, the resistance goes down. And these two components can be used for all sorts of applications where maybe these can be used to sense something. So if it gets too hot or gets too dark, we can use this to turn on other parts of an electrical circuit. Now, there are two main categories of circuits. We've got series circuits and parallel circuits. In a series circuit, we have one thing after another. In a parallel, we have separate loops, and there's different ways for the electricity to flow. Now, in a series circuit, if we were to look at the value of the current down here in this part of the circuit, we'd find that it's the same value as the current here and the same value as the current up there. So in a series circuit, what happens is I1 is equal to I2, which equals I3. We have the same current around the whole circuit. In a parallel circuit, if we were to look at I1, which is flowing down here, and we looked at I2, and we looked at I3, so that's the current through each resistor, what we find is that the current splits at this junction, and what we find here is that I1 is equal to I2 plus I3. So in a parallel circuit, we have a different current in each part of the loop. But if we were to look at the potential difference, say we had a potential difference of V1 across the cell, and we compared that to V2 and V3, that's the potential difference across these two resistors, what we find is that this potential difference is split between the components. So V1 is equal to V2 plus V3. In this circuit, however, if we've got V1 here, V2 and V3, we find that the potential difference across each loop of this parallel circuit is the same. So here we find that V1 is equal to V2, which is equal to V3. So potential difference around any loop in a parallel circuit is going to be the same. Now when it comes to looking at resistance, if we have resistor R1 and R2, in a series circuit, their total resistance is going to be equal to R1 plus R2. Effectively, the more resistors we have in the circuit, the bigger the total resistance. But in a parallel circuit, if we had R1 and R2 now in parallel, there's effectively more ways for the current to flow. So the more resistors you have here, the lower their total combined resistance. Now you don't need to calculate it, but you need to know that the total resistance is going to be less than the value of R1, and also that total resistance is going to be less than the value of R2. So now we know a bit more about the way that current and potential difference occur in series and parallel circuits. We know we've got some other equations. We can also look at the electrical power. So this is the amount of energy transferred per second. And what we can say is that the power is equal to the potential difference times the current. Now again, we measure our potential difference, V, in volts, our current in amps, and we measure our power in watts. That's the amount of joules per second that are transferred. So effectively, if you've got a component with a bigger current flowing through it and a bigger potential difference, it's going to transfer more energy per second. But sometimes we might not know the potential difference. And the other equation we can use is P is equal to I squared R. So we can also work out the power, capital P, as equal to the current squared times the resistance. Now again, you've got to remember that energy is going to be equal to power times time. And another way of looking at the energy transferred is equal to QV. So this is Q, which is a charge in coulombs, potential difference in volts, and this then gives our energy transferred in joules. So there's a whole load of different equations that you need to be familiar with that you can then apply to circuits. Now so far we've been looking at direct current, which flows one way around a circuit, but then there's another type of circuit which uses alternating current. This is the kind of thing that you might have in a household appliance where you plug something into the mains. And the UK mains is 230 volts, and it's got a frequency which means there's 50 cycles per second. If we were to look at this on a graph, this means that sometimes you've got a positive value and sometimes it's negative. And this means that the current flows one way, then the other, then the other way, then the other, then the other, then the other, really, really quickly. Now, this is used in normal kind of household appliances. And what we often have is this 3-core cable. So we have 3 different wires in the core of that cable. So the brown wire provides the alternating potential difference from the supply. The neutral wire completes the circuit, and it's the difference between the potential difference here that causes effectively that current to flow. And then finally you've got this green and yellow wire, which is called the earth wire. And this is a safety wire that means if there's a fault in the system, this carries any electricity back to the earth rather than going through your body, as it says over here. So you need to remember some of these facts about an alternating supply, especially the household supply that we have in the UK. Now the other thing that means that AC is really useful is it allows us to transfer energy over large distances, or transfer electricity over large distances, by using the national grid. Now, where can I put this? Just down here. So the national grid is a system of cables and transformers that link power stations to consumers. And what you have in a transformer is you have 2 coils of wire, the primary and the secondary, and these are wrapped around an iron core. Now when you have an alternating supply in one, it causes there to be an alternating supply in the other. And this allows us to massively increase the potential difference, but also decrease the current. And this reduces energy losses in our power supply. So you need to know a bit about the national grid and how we have step-up transformers, which increase the voltage, or we also have step-down transformers, which decrease the voltage. And finally we have static electricity. Now this is often caused if you have an insulator and maybe you rub it against another insulator. What happens then is that some of the electrons are transferred from one to the other. So that means if some electrons are transferred from this to this by the rubbing action, this thing becomes more negative, while this thing here now has an overall positive charge. And if you then separate these two things are going to have a force acting on each other. So in this case there's going to be an attractive force, but if they had the same charge they'd then be repulsive. And if we had maybe a charged sphere, and maybe this one had a positive charge, we can look at the region around it. And in the region around it where other charged objects experience a force, we say that this is an electric field. And if we were to draw the field lines around this positive charge here, they'd all be pointing away from it. Effectively, that's the direction that if you had a positive charge and you put it here, which way would it move? Well, this would be repelled. And what we find is that the electric charge is stronger near the surface. So that's it, that's AQA electricity. We've got different circuit components and how they work in both series and parallel circuits, loads of equations, as well as information that you need to understand about an alternating supply. So this video is revision of the particle model, which is something that we use in physics to explain the world around us. Now the first thing we're going to consider is something called density. Now density is basically a measure of how much stuff there is in a given volume. So perhaps we have two things which have the same volume. So I'm just going to take this off. What we have is the same volume of material here, but this one here is a lot heavier, it's got a bigger mass. And that means that there's effectively more stuff in the same space. Now the way that we work out density, we use the symbol rho, so RHO. This is a Greek letter that we use to represent density, and it's equal to the mass divided by the volume. Now because we always measure mass in kilograms and we tend to measure volume in cubic meters, this then gives our density in kilograms per cubic meter. Although sometimes if we were to measure our mass in grams or volume in cubic centimetres, we could also, depending what we're measuring our quantities in, we could maybe look at the grams per cubic centimetre. Now this particle model allows us to look at solids, liquids and gases. And if we think about the behaviour of the individual particles or molecules, this explains why certain things have certain properties. So I'm just going to consider solids, liquids and gases. So in a solid we have this close packed regular arrangement of particles. Now they're still jiggling around, they're still vibrating, but they're not really able to move around that material. So that's why a solid is what it is. A liquid on the other hand, the particles are still really densely packed together, probably a similar density to in a solid, but here they're able to move past each other. And what we have is this random motion of all the particles in a liquid. In a gas, on the other hand, the particles are really spread quite a long way away. They're moving quickly in all random directions, and because of this we can do things like we can compress a gas or whatever. So let's think about how we go from one state to another. Now if you have a solid and you heat it up, it turns into a liquid, so that's when it's melting. The liquid then might boil and turn into a gas, but if we have something which is evaporating, this is where something turns from a liquid to a gas below its boiling temperature. This is the reason that things like puddles do dry up. Even though it never gets to above 100 degrees, that water still turns into the water vapour. Going the other way, we have gas that condenses to a liquid, and then the liquid freezes to a solid. But what we also have sometimes is a solid that turns directly into a gas. You might have seen this with some carbon dioxide pellets, and this is what we call subliming. And the key thing to remember is when we move from one state to another, there's no chemical reactions happening, it's just a physical change, which means it can be reversed and they can go back to the state they were in before. Now, I said that all of these particles may be moving around and so on, and what we can then consider is something's internal energy. Now, internal energy is defined as the total kinetic and potential energies of all the particles that make up that system. So this is a combination of their potential energy, which is due to the arrangement of the particles, as well as how quickly they're vibrating and moving around. Now, if we were to look at the internal energy, so this is what this E stands for here, and we look at how that compares to the temperature, what we find is that as you increase the internal energy, the temperature also increases until we get to this point where we have a change of state. And what we find is that when something changes state, so maybe it's, in this case, the temperature is increasing, so it might be melting, it might be boiling, we have that happening at a constant temperature. Now, what we can think about are the amount, or is the amount of energy that it needs to go from one temperature to another. And what we have here, when we have these regions here, we have something which is maybe a gas, a liquid, or a solid. If we want to look at the amount of energy that it takes to heat something up, we can then look at something called the specific heat capacity. So the link between the internal energy and the temperature is that the change in internal energy is equal to mc delta theta, where what we have is our change in energy in joules. We've got our change in temperature, that's all the delta means, a change in degrees Celsius. We have our mass in kilograms, and this thing here, C, is our specific heat capacity, and that's measured in joules per kilogram per degree. But what happens when something is changing state? Here the temperature doesn't change, and there we need to think about something called the specific latent heat. And this is then defined as the amount of energy required to change the state of 1 kilogram of the substance with no change in temperature. So this is where we're looking at this region on the graph, or this one up here. And the equation that we can use for this is that E is equal to mL. Once again, we measure our energy in joules, our mass in kilograms, and that means the units for this latent heat, the specific latent heat, are equal to the amount of joules per kilogram. Now imagine this is a container that has some gas molecules in it, and what these are doing is these are moving in all directions at a range of different speeds. So that's the kind of random motion that we get in a gas. Now, provided we kept it at a constant volume and then we increase the temperature, as you increase the temperature, we're going to give these things more kinetic energy, remembering that the internal energy is related to the kinetic and potential energies of these particles in here. Now, what that means is that if you were to increase the temperature, then what would happen is that these things would have an increased store of kinetic energy, and that means that they'd be moving quicker. So their velocity or their speed also increases. And that means when they hit the side of the container, they'd be hitting it with a greater force because they're moving quicker. And what that means then is that the pressure of this gas would increase. So you have some gas, it's at a constant volume, and you heat it up, and the pressure then increases. But if we had the same amount of gas and we put it into a larger container, what we're doing there is we are increasing the volume. So let's take this gas and put it in here. Now these are still going to be moving around, but they're going to be hitting the edge of the container less frequently. And also the size of the area of that outside of the container is going to increase as well. Now what this means is that there's going to be less collisions per second, and that means that the force that they exert on the side is going to be not only smaller, but it means the pressure is going to decrease as well. So when you increase the volume for that same amount of gas at a constant temperature, it means that the pressure goes down. What we can actually say is that the pressure is inversely proportional to the volume, or we could write that as pressure times the volume is equal to a constant amount. And that's really important because it means that if you knew the pressure and the volume of some gas at the beginning, and you knew the pressure or the volume at the end after you've maybe increased or decreased the volume, we can then work out the new pressure or volume. And effectively what we can say is that the pressure times the volume before is going to be equal to the pressure times the volume afterwards. And this is provided it happens at a constant temperature. And finally, if you have this gas and you do some work on it, perhaps you compress something, so you're applying a force over a distance, what happens is you then increase the internal energy because you might be giving these things more kinetic energy. And if you give these things more kinetic energy or more potential energy, then what we're doing is we are increasing the internal energy of the particles in that system. So that is just a very quick summary of the AQA particle model. Just a little bit of revision, but if you'd like to find out more information, please have a look at my website, gcsephysicsonline.com. So everything is made out of atoms, and in the centre of an atom, what you have is this nucleus, which is made up of protons and also neutrons. And here I'm just using the yellow Lego to represent my proton. Now a proton has a charge of +1, but a neutron has 0 charge. And the size of this nucleus is actually really small. It's in the order of 1 × 10⁻14 meters. But this is surrounded by these orbiting electrons, and these orbit around it in distinct shells. Now these electrons have a charge of -1, and also what they can do is they can jump from one shell to the next, and it might be that this atom absorbs some electromagnetic radiation, the electron moves up an energy level, and then it can drop down, releasing energy as well. So the kind of scale of the atom, the actual whole atom, is in the order of 1 × 10 to the -10 meters. So these are really, really small. Now when it comes to representing these, what we do is we have 1 or 2 letters which represent the chemical element, and then we've got a number at the bottom left. Now this number here is called the atomic number, and the atomic number is the total number of protons, and that's what defines the element. And then the number at the top is bigger, and that's the number of protons plus neutrons inside the atom, and this is known as the mass number. Now when we have a standard atom, there's no overall charge, and the reason for this is that the number of protons is equal to the number of electrons, so the two charges balance each other out. Sometimes we have an ion, and this is something which is an atom which has an overall positive or negative charge, often when one of the electrons or a couple of the electrons either leaves the outer shell or a couple join it to fill up the outer shell, like you've probably learned about in chemistry. And in an ion, the number of protons isn't equal to the number of electrons, and that means it will be either positive or negative. There are also things which are called isotopes. So these are atoms of the same element but with a different number of neutrons. So that might be this thing up here. Maybe it's got an extra neutron. We still have the same number of protons, so it's still the same element, but now it's got a different mass number, and that's what's known as an isotope. Now sometimes we have unstable isotopes, and if you have an unstable isotope, it tries to become more stable by giving out particles or something from the central nucleus of that atom. And there are a few different sorts of radiation. First of all, we have alpha radiation. This is made out of 2 protons and 2 neutrons, and that means it's relatively heavy, and it's also very ionizing. It's got a charge of +2 because of these 2 protons. And when we talk about things which are being ionizing, effectively that means if they smack into another atom, they can knock off electrons and make the atom into an ion. Now that can be dangerous for people because that then changes the chemical properties and can cause mutations and cancer and so on. So first of all, alpha radiation emitted from the nucleus, very heavy, and it's got a very short range. The next type is beta. And beta radiation is a high-speed electron which is emitted from the nucleus of the atom. This has got a charge of -1 because it's an electron, and actually what's happening inside is that a neutron turns into a proton and an electron. So this is then emitted. It's quite ionizing still because it's got a charge of -1. It's got a longer range than alpha, but it's not as dangerous because it's not got such a big charge. The third type is gamma radiation. Now this one here isn't actually a particle, instead it's a burst of electromagnetic radiation. It's a wave, and that means it's got no charge. It is ionizing because this wave can still cause electrons to be taken off another atom, but it's also got a really, really long range, and it's really hard to stop gamma radiation. And occasionally, sometimes we also get neutrons which are emitted. And once again, the neutron, what it's going to do, it's just going to disappear from that nucleus. It goes flying off, and maybe some of the energy of this neutron could cause something else to become ionized. So neutrons, again, have no charge. That's a kind of sort of fairly rare kind of nuclear radiation. But what we can do is we can show these with some nuclear reactions, a bit like the way that we show chemical reactions. Now, the way that we show alpha in terms of this nuclear reaction is we maybe start with a radioactive isotope, and what happens is it gives out an alpha particle. Now we give the alpha particle, because it's the same as a helium nucleus, because it's got 2 protons and 2 neutrons, we can often represent an alpha particle as He for helium-24. Now what happens is that this number here, the atomic number, goes down by a factor of 2, because we've got rid of 2 protons, so it's Z-2. And the mass number goes down by 4, because it's got rid of 2 protons and 2 neutrons. So the number at the top goes down by a factor of 4. And this then makes a new isotope. If we did the same and looked at beta, again we might have an element X. You know, this is just a made up thing. And what happens if it gives out beta radiation? This is the same as an electron. And effectively an electron, we give it the number of 0 and -1. I'll talk about why that is in a second. Now this thing here might decay and it might make a different isotope Z. Now the mass number doesn't change, because all that's happening inside is that a neutron turns to a proton, so it's still got the same mass in the middle. But because we now gain one proton when there was a neutron before, that means the number at the bottom increases by 1. And what we can see is that this number here and this number here add up to that number there. So what we're doing is we're conserving the atomic number and mass number in this reaction. So this is a way to represent beta emission. Now when it comes to looking at radiation, there are two things we can think about. We've got activity, which is the amount of alpha or beta particles which is given out. So that's the amount given out per second. But what we then do is we actually count this using some kind of radiation detector, often a Geiger-Müller tube. So count rate is the actual number of decays recorded each second by the detector, while activity is the total amount given out from that nucleus. And actually the thing about radioactive decay is it's something which is spontaneous and random, and there's nothing that we can do to influence. But what we can do is we can look at the decay of something over a period of time. So maybe we have the activity or the number of nuclei up here, and here we have time. And what we find is over time we get a graph that looks like this. And the important thing is that if we look at a certain amount of time and we look at the activity, after a certain amount of time the activity is going to decrease by half. After the same interval again, the activity decreases by a half, and again after the same interval it decreases by a half. And this time down here is what we call the half-life. And there are really two ways that we can define this. Either the time it takes for the number of nuclei of the isotope to half, or the time it takes for the count rate or activity in the sample to half, to fall at half of its original level. So these are two definitions you need to know about. And effectively what this means is that it doesn't mean that after 2 half-lives everything is gone, it just halves and halves and halves and halves. And this line kind of never really gets to the bottom. And there are two further things we can think about, which are irradiation and contamination. Now, irradiation is basically you expose something to nuclear radiation, but that doesn't mean that thing then becomes radioactive. We can actually expose food to radiation to kill the nasty germs, but it doesn't make the food radioactive. However, contamination is when you actually get some of these radioactive particles mixed in with whatever the sample might be, and then that thing then continues to emit radiation and is contaminated. Now, we haven't always known about radiation and what it's like inside the atom. In fact, there are different models which we've actually used over time. Initially, they thought that all atoms were just these small indivisible spheres, that we couldn't break them down any further. Then we went on to the idea that maybe when we've got these electrons, maybe we've got all of these electrons and protons all mixed up together. And this was known as a plum pudding model. But it was later on when they did an experiment where they had a sheet of gold foil and they fired alpha particles at this gold foil. And what they found was that most of the particles went straight through. So if most of the particles went straight through, that means most of the atom is empty. Now they also knew that these alpha particles were positive, and some of these positive particles actually bounced back. Now the only way that you can have a positive particle bounce back is if it bounces off something positive inside the atom. So this meant that we then knew that there is this dense positive core. And this then led onto the model where we have the dense positive core of an atom, and this is surrounded by mostly empty space and a sea of charged electrons all around it. And then later on they found that actually there were neutrons in the middle as well, and then since then we've looked at other models where we look at the waveform of these particles. All gets a little bit confusing. Now the thing is that we are constantly being exposed to radiation, and some of this is called background radiation, and this comes from a number of different places. So some of this is natural and we can't get away from it. We have cosmic rays, which are highly charged particles coming from space. There's also radioactive isotopes underground which decay, and this gives us some radiation from the rocks beneath our feet. But we also have it from man-made things. Some of these are nuclear accidents in power stations, some of it's from nuclear testing of atomic bombs, and also in medical uses. Now the thing is with medical is that we can use it for a couple of things. Now we can use radioactive tracers to actually find the cause of disease and illnesses. So you maybe inject a tracer, which is a gamma source, and then we can put a detector outside the person, and we can then use that to work out maybe where their blood is flowing. And you want to make sure that if you're using a medical tracer, we use something with a short half-life. On the other hand, you might be using something to treat things, so maybe we're trying to blast that cancerous cells with a high source of highly ionizing radiation like alpha particles. we can direct that at the cancerous cells in order to kill those. So we can use radioactive material both to kind of find things in the first place and also to treat things. Now, the other thing that we can do with some isotopes is we can actually split them apart. And when we split them apart, they release lots of energy, which in the end causes water to heat up, turn into steam, turn turbines and turn generators, which we can then use to make electricity. Now, the way that we do this is with something called nuclear fission. So fission, with two S's, is when you split heavy things up. And we do that by firing a neutron at it. When the neutron then joins that nucleus, it becomes unstable. It splits into two kind of big other kind of daughter nuclei, and it also releases further neutrons. So what we're doing is we're basically taking something big, we fire a neutron at it, and then it splits apart and it releases more neutrons. Now, this process is called nuclear fission. And if we could then capture another one of these neutrons in another, maybe uranium or plutonium nucleus, this would then cause another reaction and another and another. That's then called a chain reaction. Now, this is a great way of generating electricity because there's no carbon dioxide which is emitted. One of the big problems is that these daughter products are then really radioactive, and they've got a radioactive half-life which could last hundreds of thousands or even millions of years. There's also the issue that if there is a problem with this and we get a nuclear accident, it affects a lot of people, like at Chernobyl and Fukushima. Another thing that we can do though is we can take really light things, and this is when we join really light things together, and this is nuclear fusion. So in nuclear fusion, you might join two protons together, and as you add protons together, we then end up by making helium. Now, this is brilliant because there's no radioactive waste. The problem is that we can't actually use it on Earth at the moment to generate electricity, but nuclear fusion, when we join light things together to make heavier elements, is what happens in the sun and all of the stars, and that's why they keep emitting light. So that's just a quick recap of atomic structure for AQA. So this is revision of the AQA forces topic. Now, the thing about forces is they are measured in the Newton, and there are really two different sorts. We have contact forces and non-contact forces. So contact forces are where you have two surfaces in contact. So we're talking about friction, air resistance or drag. You've got the tension, which is maybe when something is being pulled, like a spring. And then normal contact force, I'll come on to in a little bit of time. Non-contact forces, they can act over a distance. So we might talk about the gravitational attraction between two masses. Maybe if you've got a negative and a positively charged object, you've got some electrostatic force or the magnetic force as well. Now, the thing about forces is that these are vectors. And a vector is something that has size and direction. And what that means is we can then represent a force with an arrow, where the length of the arrow tells you about the size of the force, and the way the arrow pointing is telling you about the direction. That's different to a scalar quantity, which only has size. Now, something that often causes confusion is the difference between mass and weight. And weight is a force, and that's caused by the mass of an object in a gravitational field. So like I said, we always measure our weight in newtons, we measure our mass in kilograms, and that means that the gravitational field strength is measured in newtons per kilogram. And this field strength really depends about which object we're considering. On the moon, for example, it's about 1.6 newtons per kilogram. On Earth, it's about 9.8 newtons per kilogram. So if you need to convert from kilograms into newtons, you just multiply by 9.8. Now, in order to actually measure the weight of an object, what we can use is a Newton meter. Whereas I suppose, strictly speaking, if you want to look at the mass of an object, we should use a mass balance. And that would then give you a value, often in grams or kilograms. And you've got to remember as well that the weight of an object, this acts at the centre of mass. Now, the thing about forces is that if we have an object, which I've just got here, and maybe there's a 5 Newton force acting to the left and a 10 Newton force acting to the right, what we can do is we can replace both of these arrows with a single arrow to show the overall force acting on the object. Now, if you've got 10 Newtons that way and 5 Newtons that way, that means overall there's going to be a 5 Newton force acting to the right. And this is what we call the resultant force. And this is really useful if we think about real objects. Perhaps we just have an apple which is just sat on the desk here. At the moment it's not moving, and that means there's going to be a balanced overall force. what we can do is we can maybe draw a diagram of the same thing. So this is my apple, and what we might find is that there's a force acting down. In this case, it would be the weight of the object. And then there's another force, which is an equal size arrow but in the opposite direction. And this one here fits this is now the force of the desk pushing back. And that's what we call our normal contact force. Now if we had another object which maybe had a force in this direction and a force down here, we can again look at the overall force. And what we can do then is add up these two vectors together. And effectively, if I just put in a line like this, the resultant force of these two arrows, because there's one to the right and one which is down, is going to be to the right and down. So this again is another way of showing that resultant force. And because it's a vector, we're also often interested in the angle that force is acting in. So it's not just the size of the resultant force, it's also the direction that it's acting in. Something we can do which is similar to this is maybe we had a force acting at a certain angle, I'm going to call that theta. We can also resolve this force into its vertical and horizontal components. So if there's a force which is acting up and to the right, effectively there's a size of a force acting upwards and a certain size of force acting to the right. And we can see again how the length of the arrow to the right is the same as the size of how much that arrow there goes to the right. Hopefully that makes sense. I will have some more videos that explain this in a little bit more detail. But drawing diagrams is a really useful way of maybe looking at all the forces on the object, finding out the resultant force, and then finding the size and the direction of that resultant force. Now the other thing about forces is if we have an object and we apply a force to it over a certain distance, we're then doing work. So this thing here, work, is quite an important concept. And if you want to look at the work done on an object, I'm going to call that W, so this is the work done, that's equal to the force applied multiplied by the distance that it goes. So in the case of moving this Lego block, we need to think about how far it's travelled in the direction of the force and the size of the force. Now, work done and energy transferred are both measured in joules. We've got our force measured in newtons and our displacement, the distance that it travels in the direction of the force, is measured in meters. And this then gives us the definition of what 1 joule is. So 1 joule is the work done when a force of 1 newton causes a displacement of 1 meter. The next thing we're going to look at is forces and elasticity. And basically this might be when you're bending, you're compressing or you're stretching an object, and especially the normal kind of standard spring that we have here. Now if it's elastic, it means it goes back to its original shape when the force has been taken off. However, something which is inelastic, perhaps a spring that is bent too much, it doesn't return to its original shape, and then it's not elastic anymore, it's inelastic, or we can also call that plastic. Now for that spring, the force applied is going to be proportional to the extension of it. Extension means how much longer it's got. In fact, there's an equation that we use which says that force is equal to K times E. So again, we measure our force in newtons, our extension in meters, and this then gives what we call the spring stiffness. That has the units of newtons per meter. Now that's the amount of force required to extend something, but if you do extend something, that spring can then store some energy in the elastic potential store. And we can also look at the equation that says the elastic energy stored is equal to a half KE squared. So this really depends on how stiff that spring is and how much it's been extended. So again, this one is a force which is measured in newtons, but this is the energy stored measured in joules. Now, if you apply a force at a distance from an axle, you can then cause some rotation, perhaps the wheels of a car or maybe the steering wheel inside. And what we can then consider are moments, levers and gears. Now, the turning effect of a force is what we call the moment, and it's basically equal to the force multiplied by the perpendicular distance, that's important, the word perpendicular, distance from the pivot to the line of action of the force. So what we're saying here is that the moment, which is capital M, is equal to the force times distance. And here I'm going to use d for distance to show it's that distance from the axis. Now, because we measure force in newtons and our distance in meters, this gives our moment in the unit of the Newton meter. That's very different to the newtons per meter that we have for our spring constant over here. Now if you have an object which isn't rotating but it's balanced, what we can then say is that the moments which are going clockwise are equal to the anti-clockwise moments. And if I just put that in shorthand over here, we can say that the clockwise moments are equal to the anti-clockwise moments if it's balanced. Now in the simplest example, you have some kind of seesaw. If you know that there's a certain force at a distance, maybe going anti-clockwise, and you know the size of the force that you can apply, you can then work out the distance that you need to apply that force to make sure that this thing here is in equilibrium, it's balanced, and it's not rotating. Something that we also need to consider is pressure. And this is the pressure in fluids. So it could be things like gases or liquids. Now to calculate the pressure at the surface of a fluid, that pressure, which is small p, is the amount of force per unit area. Now by convention, we measure our force in newtons, our area in square meters, and that means the units for pressure are newtons per square meter, but we can also use another unit, which is a Pascal. That's capital P, small a. So if we're using our force in newtons, area in meters squared, we can then also give our pressure in pascals. For example, atmospheric pressure, the kind of pressure of the air which is surrounding you and me at the moment, is 101 kilopascals. So when it comes to pressure, we often have very big numbers. Now we can also think about the pressure in a column of liquid. Now really, the deeper you go down, so the greater the height that you go under the surface, the more water there is going to be above you, which is pushing you down. So as you go deeper and deeper, the pressure increases. It also depends upon which liquid you have. Water isn't particularly dense. If you had a column of mercury instead, because there's more stuff in a certain volume, the density of that material also affects the pressure that you're going to feel. And finally, it really depends upon where you are in the galaxy. If you went to Jupiter, or one of these big planets with a bigger gravitational field strength, you'd also then get a greater pressure as you went under. So we can say that the pressure is equal to rho GH. So the pressure depends upon the density, the gravitational field strength, and the height. Density is measured in kilograms per cubic meter. Gravitational field strength is newtons per kilogram. The height is in meters. And again, the density, hopefully you can see this, is measured in pascals. Now, if you submerge an object in this liquid here, there's going to be a force acting upwards on it. This is called upthrust, and it's because there's a difference in the pressure at the top and the bottom of that object. And this is the reason that things like ships, for example, they still float in water. So upthrust, or buoyancy, is a force that acts in a liquid or a fluid on objects. So I'm beginning to run out of room, so let's go onto this page here. The final thing is atmospheric pressure. Now the atmosphere is basically above the Earth's surface, so this is supposed to be the Earth down here. There's a very thin layer of gas. Now as you go higher and higher, the density of this decreases. Now because pressure is caused by the impact of these particles on the surface, if you've got less particles impacting, that means as you go higher and higher, we go from a high pressure down here, and as you go higher and higher, the pressure gets smaller and smaller. Now the next thing to consider is motion of objects. Now we've already heard that there are scalar quantities which just have size, and also vector quantities that have a size and direction. Now a good example of a scalar quantity is speed. So speed is just how quickly something is travelling. And these are just some of the speeds of everyday objects. So if you're walking along, it means that you're going at 1.5 meters per second. So every second you go another 1.5 meters. You also maybe need to think about things like the speed of sound, which is much quicker. So sound travels at 330 meters per second, depending on kind of exactly where you are in terms of the atmospheric conditions. But things like light and other electromagnetic waves, they travel at 300,000 meters per second, so even quicker than that. Now, scalar quantities also include things like distance, but there's a vector equivalent called displacement. And this includes not just the distance that something is moved, but also how far the direction that it's moved from its start point. So vectors always have a direction as well. Another vector quantity, a bit like speed, is velocity. And at GCSE we define velocity of an object as the speed in a given direction. And we can also look at how quickly this velocity changes, which is then our acceleration. Now looking at the relationship between distance and speed, we can say that s is equal to vt. Now this is confusing. We don't use the letter s for speed. That's just something that we don't do. Instead, we use the letter v to represent speed or velocity, and this is measured in meters per second. S actually stands for our displacement. So think about the S for displacement, or the S in distance. So S is our distance in meters, and then time is in seconds. Now, another more useful way of looking at this equation is that V is equal to S divided by T. So the speed is equal to the distance divided by the time taken. And if you want to work out how quickly something is going, you simply need to measure the distance that something's gone and then time how long it takes to go that distance. Now, there's one little interesting thing about velocity if you're doing the physics, and that basically means that you can have something where something's velocity might be changing, but its speed stays constant. And this is where you've got something which is moving in a circle. So maybe you've got an object and it's rotating in a circle. It might be going 5 meters per second, so it might have the constant speed, but its direction is constantly changing. So sometimes it's going left, sometimes it's going down, sometimes it's going right, and then sometimes it's going up. So when you've got circular motion, this is a special case where you've got an object which has a constant speed but a changing velocity. Now, something which it's really useful to do is to draw different graphs to represent an object which is moving. Now, one of these is called a distance time graph. So we measure our distance in meters up here, and we have our time in seconds along the bottom. And what we might then do is plot some data for an object, and we can see how its distance changes with time. Now, on this graph here, the gradient of that line is equal to how quickly the distance changes per second. And that means the gradient is equal to our speed, v. Sometimes, however, you might get a curvy line, and then in order to work out the speed of that object or the velocity of that object from this line here, what you then do is you draw a tangent to that line. Once you've drawn a tangent to that line at the point that you're interested in, you can then measure the gradient by looking at the change in y and the change in x values, so you can actually then work out the value of the speed on this curved line. Another type of graph which is really useful is the VT graph. So this is our speed in meters per second, we've got our time in seconds here, and again what we can then look at is maybe how an object's velocity changes over time. Now, for this graph here, the gradient is going to be equal to the rate of change of velocity. We're looking at how quickly that velocity changes per second, and that means our gradient is then equal to our acceleration. And actually, the equation that we can use to work out the acceleration of an object is equal to the change in velocity divided by time taken. So for this, we measure our velocity in meters per second, our time in seconds, and that means our acceleration then is the amount of meters per second per second. So the units for acceleration are meters per second squared. And we can often find that from a VT graph by looking at the gradient. And if we actually look at the area under this VT graph here, the area is equal to the velocity times the time, which we saw over here, the velocity times the time is equal to the distance travelled. So under a velocity time graph, the area is equal to the displacement. Now, when we look at the change in velocity, what we're really looking at is the difference between the final velocity, which is v, and the initial velocity, which is u. So we can also say that this change in velocity is equal to v minus u. But now we can actually introduce another equation which says that v squared minus u squared is equal to 2as. So this one here looks a little bit confusing. Effectively, this is our final velocity in meters per second. Take away our initial velocity in meters per second. Often this is just 0 in lots of equations that you might, or questions that you might be given. A is our acceleration in meters per second squared, and then our time here is in seconds. Sorry, our distance is measured in meters. So if you get a question and you can identify what you know from the question, you can often decide which equation you can then use to work out your final answer. Now, if you had an object which starts falling, initially it's going to accelerate quite quickly and it's going to get faster and faster. Now, for the apple falling towards the ground, there's going to be a constant downwards force called weight, and this doesn't change. But its air resistance increases as this gets faster and faster. In fact, if we were to plot a graph, a velocity time graph of the motion of a falling object under gravity, especially where you've got air resistance, we'd find that the graph does something like this. Now, the reason for this is that it gets to a point where its velocity doesn't get any quicker. And this point here is where the object has reached terminal velocity. And when the object is travelling at terminal velocity, there's no resultant force, so the weight in this case is going to be equal to the air resistance. I'm just going to put that AR for air resistance. That means there's no net force on it and it doesn't get any quicker. Now there are 3 Newton's laws that you need to remember. Now Newton's first law basically says that if there's the resultant force acting on an object is 0, so there's no resultant force in it, then stationary objects remain stationary, but things which are moving continue to move at the same velocity. So for example, if you've got a racing car which is travelling as fast as it possibly can down a nice straight road, there's going to be a point where the air resistance is equal to the thrust of the engine and it doesn't get any faster. We then have Newton's second law. Now basically this says if there is a resultant force on an object, then the object is going to accelerate. And the size of that acceleration really depends upon the mass of the object and also the force that's being applied. So we can often write this as F equals ma. Now this is just the equation form of Newton's second law. So we've got our force in newtons, our mass in kilograms, and our acceleration in meters per second squared. And again, just to say that the acceleration of an object is proportional to the resultant force in it. So you get a bigger acceleration for a bigger force, and it's inversely proportional to the mass of the object. So that means that you get a smaller acceleration when you have a bigger mass for a certain force that's been applied. And then finally, we've also got, to complete the set, Newton's third law. And this simply states that whenever 2 objects interact, the forces they exert on each other are equal and opposite. So what that means is if we have the moon, for example, and this is being attracted to the Earth at the moment, the force of the attraction of the Earth on the moon is the same as the force of attraction of the moon on the Earth. And what we then have are a force pair. So that's Newton's third law. So a way to think about this is that if the force is equal to 0, then objects which initially were had no velocity stay at 0. Objects that were moving still keep moving at a constant velocity. Here, if there is a force, then that force is going to be causing an acceleration. And here, what we're saying is that if you've got an object A and an object B, the force that they exert on each other are going to be equal and opposite. And here the mass is what we often call the inertial mass. And that's basically because things which are still want to stay still and things which are moving want to stay moving. And this inertial mass is basically their resistance to wanting to change what they're doing. And if we want to define inertial mass, then we pretty much define it as the ratio of force to acceleration for an object. Now I've pretty much run out of room again, so let's continue this on the page below. So the next thing we need to look at is the stopping distance for a vehicle. Now this is basically the total distance that a vehicle travels, which includes the driver's reaction time when they're thinking about and actually reacting to something they might see ahead, and then the distance that the car then, or the vehicle then takes to stop. So this is your stopping distance. Now the thinking distance is going to be affected by things of the driver. So this might include things like tiredness, by alcohol, by drugs, both legal and illegal, and also things like distractions, including mobile phones. So that's what's going to affect how quickly the driver reacts. But once they put the brakes on, that factors that affect how their braking distance might be applied, might be changed, include the condition of the roads. So it could be something which is maybe wet or icy. We're thinking about the condition of the tyres and the brakes. And of course, these and the total stopping distance are also going to be affected by how quickly that car is going. Pretty simply, the faster you're going, the bigger the stopping distance is going to be. And if we think back to the energy topic, the reason that a vehicle is slowing down is because there's a couple of brake pads which go onto the brake inside the wheel. And what this is doing is then transferring some of the initial kinetic energy store of the car into the thermal energy store of the brakes, which get hotter, and also the surroundings, which heat up as well. Something we also look at is momentum. And momentum is simply defined as the mass times the velocity. So momentum, confusingly, has the symbol little p for momentum from the word impetus, and this is equal to mass times velocity. Now for this, we measure our mass in kilograms, our velocity in meters per second, and that means the unit for momentum are kilograms meters per second. Now this is also a vector quantity, because it really depends on the direction that you're going, and you might have maybe a positive momentum or even a negative momentum. And it's really important that you try not to get momentum confused with kinetic energy, which also depends on the mass and the velocity of an object, but that then has a unit of joules. Now, in a closed system, what we can say is that the total momentum before an event is equal to the total momentum afterwards. So what we can say is that the momentum before is equal to the momentum afterwards. Now, if you're doing the full GCSE Physics, you might need to do some calculations as well. So perhaps you had an object which is travelling along and it hits a stationary object and the two things move off together. If you know the total momentum of that moving object at the start, you can then work out the total momentum of the two things that move off together. So it might be that you're looking at the mass of an object times its initial velocity, and this is then going to be equal to the total mass times the combined velocity at the end. So this is where it's worth spending a bit of time doing some calculations and actually practicing a few questions about this. Now, the other thing is that we've already seen the equation from Newton's second law that F equals ma, and also that a is equal to the change in velocity divided by time. So what I'm going to do is combine these two together, and I'm going to replace this a with this term over here. So we can then say that F is equal to m times the change in velocity divided by the time. And if you've got the mass times the change in velocity, then this is also then equal to the change in momentum. So we can then say that the force is equal to the change in momentum divided by time. And what this basically says is that the force is equal to the rate of change of momentum. So what this means is that if you had a collision or something or an impact, if you change the momentum of an object more slowly, less force is going to be felt by that object. So this is why we have crumple zones on cars, it's why we have airbags, it's why we have soft pillows. Because what you're doing is you're still changing that momentum of the object, you're still slowing it down, but if you slow it down slower, it's going to experience less force. And that then means that there's going to be a less effect on maybe people involved in real life scenarios. And finally, that's it. We've done all of the forces topic for AQA GCSE. It's been a big one. Hopefully there's been something here which has been useful. Thanks for watching. So this is revision of the AQA waves topic. Now what waves do is that they transfer energy. And there are really two different classifications of waves. We have longitudinal and transverse. Now these longitudinal waves, what they have are the particles in the wave. These are vibrating maybe back and forwards in the same direction that the energy is being transferred. So if energy is being transferred this way, the particles are just going backwards and forwards. In a transverse wave though, the particles are going side to side and the energy is being transferred at 90 degrees. And examples of a longitudinal wave might include things like sound and ultrasound, but for a transverse wave we have the whole of the electromagnetic spectrum. So that includes things like light, we're going to come on to that very soon, but also we have things like the water ripples on the surface of water. Now if we were to look at the position of a load of particles along a certain bit of something which is vibrating, there's a wave travelling, what we can look at is the distance of the particles from their rest position. And this distance here is what we know as the amplitude. Okay, and so amplitude is the distance between where the particle normally is and how far it vibrates up and down. There's also a distance which is one complete wave cycle, and this is known as the wavelength. And we give the wavelength the symbol lambda, which is a Greek letter, a bit like an upside down Y, and this represents our wavelength. So we define the amplitude of a wave as the maximum displacement of a point on the wave away from its undisturbed position, while the wavelength is the distance from a point on one wave to the equivalent point on the adjacent wave. So it could be peak to peak, could be trough to trough, or maybe this point to this point. Now if we think about a wave, there's a link between how long it takes for each wave and the amount of waves per second. So the amount of waves per second is the frequency. So we can see now that there's a quicker, higher frequency here, but each wave takes less time. And what we can look then is the link between the time period for a wave and the frequency. We find that the time period of a wave is equal to 1 divided by the frequency. Now for this, we measure our time period in seconds, and it's capital T for time period. and we measure our frequency, which is the number of cycles per second in hertz. So that frequency of a wave is the number of waves passing a point each second. The other equation that is really important to know is known as the wave speed equation, and this says that v is equal to f times lambda. So v is our wave speed. This is measured in meters per second because it's just the speed. We measure our frequency in hertz, and the wavelength, because it's a length, is measured in meters. And with this information here, it allows us to maybe look at things if we're measuring real waves. It might be as simple as we're measuring the speed of sound, where what you have is maybe two people who are a certain distance apart, and you can make a signal between these two people, and if you know the distance between them, which is s, maybe they make a signal and they record the signal that person's doing. Maybe they're clapping their hands or bursting a balloon. They can actually time the time it takes for that sound wave to get to them. And then you should remember that the speed is equal to the distance divided by time. Now you can do something similar with maybe a water wave in the tank. Maybe if you knew how the wavelength of that and you knew the frequency, you could then work out the speed of those ripples. Now if you have another material and a load of waves are approaching it, so this is the direction that the waves are coming in at, sometimes those waves can be reflected, which means they bounce back. Sometimes they can be absorbed, which actually means they're stopped, and sometimes they are transmitted through that material. But as they go through that material, certain things change. It might be that their wavelength decreases or their speed decreases as well. Now in the simple case, if we think about what happens to reflected light, and I've just got a mirror here, we can draw a mirror like this. So I've got the shiny side here, and this is the dull side. We can then draw our rays of light, which is maybe showing the direction that wave is travelling. So maybe this is a light wave, and then this is reflected. Now this line here at 90 degrees to the surface is called the normal. And in this case, if we're maybe thinking about a ray of light, this would be the incident ray. So this is the angle of incidence. This is the reflected ray. So that's the angle of reflection. And these are always measured between the ray of the wave or the light and the normal. Now the next thing we can maybe consider is sound. Again, this is our longitudinal wave, and it has an approximate value of about 330 meters per second in air at ground level. Obviously that changes as you go higher, and it gets a lot quicker if you're looking at sound in a solid. Now the reason that sound travels is because we have vibrations in particles. These ones here maybe start to vibrate or oscillate backwards and forwards, and they pass their vibrations on and on. And what we have then is in a sound wave, you have regions where we have the air which is compressed, and regions where the particles have separated, which is called rarefaction. And humans and all animals, we use our ears to hear things. So this is my diagram of the ear. Now you've got the air particles which are vibrating, and basically this is the ear canal here, and they then cause this part here to vibrate. So this is the eardrum, and this passes these vibrations onto the fluid here, which causes these bones to move, and then that then sends an electrical signal down this nerve here into the brain, which is when we then detect a sound. Now the thing is that this can only vibrate over a limited range of frequencies. For the human, it goes from 20 to 20,000 hertz. So anything above this, any sound waves which are higher than this, we can't detect. So sound waves that we can't hear have a frequency greater than 20 kilohertz. And this is what we then call ultrasound. Now with ultrasound, we can actually use this to look inside things that we can't see. Now a very simple example would be if you had a pipe, and the pipe had a crack in it, maybe somewhere in that pipe. If you had a transducer here which sent down an ultrasound wave, the wave would travel down the pipe, and when it gets to a boundary, which is where two things meet or where there's a crack, what we then get is a partial reflection. So some of the wave might pass through, but some of the wave would bounce back. Now what we can do is we can actually record the time that the detector then works out when the signal is coming back. If we know the time it takes, and we also know how quickly these ultrasound waves actually travel through that material, we can then work out the distance, because the distance we can work out from s is equal to vt. Now the careful thing you've got to make sure is actually that's the distance to and from the obstruction, and so you'd have to divide that by 2 to find the actual distance from here to there. Now the same things work if we're looking at inside mummies' tummies and we're looking at maybe scanning babies. Again, what we can do is, because these are completely safe, we get a partial reflection from the baby inside the mother, and that allows us to then actually build up a picture of what that baby looks like and actually kind of check their kind of how they're getting on in terms of if they're developing properly, and also if it's a boy or a girl. Now, another type of wave that we can look at are seismic waves, and these are things which happen when there's an earthquake or some massive movement underground. Okay, this is not a great circle, but this is supposed to be my picture of a cross-section of the Earth. And so maybe there was an earthquake at this point up here. What we'd then have two sorts of waves. We'd have our primary waves and our secondary waves. So these are called P waves and S waves. Now, the P waves are longitudinal, and that means that they can travel through liquids and solids. But the S waves are transverse. And that means that they don't work going through liquids because of the way the particles move, so these can only go through the surface. Now, the centre of the Earth is there's this kind of molten kind of region around here, and what that means is that S waves can basically travel through the mantle and the upper parts of the Earth. So this is maybe where we're detecting S waves, but P waves can actually travel straight through the middle, and they do get refracted slightly, but basically these P waves can travel from one side of the world to the other. And by detecting these waves, we can actually then work out, sort of looking backwards, at the structure of the centre of the Earth. So seismic waves often caused when parts of the Earth move and there's maybe some kind of earthquake. We detect the primary and secondary waves at the surface, but it's what they travel through beforehand and where they end up that then tells us about the structure of the Earth beneath us. But now let's look at the electromagnetic spectrum in a bit more detail. So the electromagnetic spectrum is a whole series of waves, and all of these travel at the same speed through a vacuum. This is also the speed of light, which is 300,000 meters per second. So that's pretty quick. And there are 7 main categories of waves that we're interested in. And so we go from radio at one end through to gamma at the other. So you've got radio waves, microwaves, infrared, which means below red. Then we have visible light, and because you've got infrared and then visible, that means we start with red waves, which are the longer wavelength, and then we go Royabiv to violet light at this end of the spectrum. We then go beyond violet into the ultraviolet. We then have X-rays and then gamma rays. And gamma rays are again this thing which are emitted by the nucleus of an atom. Now basically, as we go this way through the spectrum, what we find is that the wavelength lambda decreases, but also as we go along this way, the frequency increases. And what we find is that when you have higher frequency electromagnetic waves, they're going to be more dangerous. We can say they're more ionizing. And really from this point onwards, what we have is ionizing waves. Now what that means is that ultraviolet isn't great for you, X-rays are worse, and gamma is worst of all. So that as you have a higher frequency, the waves become a little bit more dangerous. So why is it that you need to know about this? It's because these have loads of uses. For example, if we think about radio, this is used for television and radio, so used for communication. We also use microwaves for communication, and this might include things like your mobile phone, but also we have satellite communication. And we can also use this to heat up food because it causes certain molecules to vibrate at the same frequency. So we can also use this for heating up food in your homes. When it comes to infrared, we can use this for heating because infrared is just a type of heat radiation. And we can also use it for night vision, so perhaps you have cameras that can see in the dark. Visible light, used all the time, including things like fibre optic communication. So that's how you get your broadband nice and fast. We then have ultraviolet, which is used for energy efficient lamps and also for sun tanning, so if you want to get bright orange. Running out of space here a little bit. Now X-ray and gamma, both really high frequency. These can be used for medical uses. So they can be used to actually scan the body to find out where something's gone wrong. Maybe using a conventional X-ray, maybe a CT scan, or maybe some radioactive tracer. But they can also be used to actually blast away at the damaged parts of the body to actually maybe reduce cancer, for example. So here are just some uses of different parts of the electromagnetic spectrum. Now, something else that light does is it refracts. So refraction is when you have a wave and it meets a different medium, so it might be a different substance, and then it changes direction because it changes its speed. And you might get perhaps a glass block or a perspex block, and you shine a ray of light at a certain angle, and this hits the surface here, so this is my normal. What happens then is that this changes direction through the medium, and then when it comes out the other side, it then goes back into the original direction. So this is called refraction. And the reason for this is if we were to maybe zoom in on this part over here, where we had the waves hitting the surface, if we think about the wave fronts hitting that surface, one side of the wave is going to hit the surface before the other. And as it hits the surface and slows down, it does something a bit like this. So it starts to slow down on that side still moving. And then that means it all, as one, because effectively one side is slowing down before the other, it changes direction. Now that's maybe not so obvious, but if I put in this line here to show the direction of that wave, what we can see is as the wave slows down, it changes direction. The next thing I'm going to look at is lenses. Now there are two main sorts of lenses. We have lenses which are shaped like this, and we have lenses which are shaped like that. Now this type here that bulges in the middle is called convex, and the one that has a dip in the middle is called concave. Now this might be familiar if you're short-sighted and you look at your glasses, they look a bit like this. If you're long-sighted, your lenses are slightly fatter in the middle. And these work by refracting light. So as light comes in, because it's slowing down, it changes direction, like we saw over here. And depending on the shape of the lens, we either make the light come together at a point or the light splits apart. And we can use that when it comes to drawing ray diagrams. So for a concave lens, this is how we represent it on the diagram here. If you've got an object a long way away and we look at the rays of light that come from the top of the object through the lens, it goes through the focal point, and when rays of light cross over, we then see the image. So that's if you have a convex lens and you've got an object which is a long way away. If, however, the object is a lot closer, we still construct the ray diagram in the same way, but here the image is now formed behind the object, and it's actually made out of virtual rays, so what we see is a virtual image over here. This one is enlarged, and this is the way that a magnifying glass works. But with your concave lens, what we have is, again, if this is our object over here, the ray of light, when it goes through the lens, it actually then bends away from this principal axis over here. I've got videos that explain this in a lot more detail because it does take a while to actually get used to this. But basically when you have a concave lens, the image that we see is smaller and it's a virtual image. And if we want to look at how the image size compares to the object, we can look at the magnification. I'd also like to look at colour, and we're thinking about colour in terms of the visible part of the spectrum over here. Now each of these colours has its own frequency and wavelength, and they behave in a certain way as they may be going through either filters or maybe they're bouncing off a surface. Now a green filter will only let green light through, and a red filter will only let red light through. That means if you put the two together, because no red or green light is going through, basically no light gets through at all. We can also see that by, if I have this green laser over here and I can shine the dot here, if I shine the green light at the green filter, all of that light just gets through. You can see that it just, even though it's hitting the filter, all of that light is getting through. If, however, I shine that green light at a red filter, it doesn't get through anymore, because what's happening is that the red filter is absorbing all of that green light. But if you had maybe a red object like this, why does it appear red? Well, because this object here is reflecting any red light. Now white light that's landing all over this video at the moment, that's made up of all of the colours of the rainbow up here. But this thing here, it's absorbing all of the other colours, but it's reflecting the red light. This green block, on the other hand, that's absorbing all of the colours of light apart from green, which it's reflecting. Now if you had a white object, it would be reflecting all of the colours. If you had a black object, it would be absorbing them all. And this brings us nicely onto a black body. Now in physics, a perfect black body is something which absorbs all of the radiation landing on it. So that means all of the light, all of the infrared, it absorbs it all. It is also a perfect emitter, and that means that it gives out this radiation really quickly. And this then links back to the Earth, because the Earth, if it's absorbing radiation, and there's going to be energy that we absorb that's transmitted from the sun, if we're absorbing more than we're emitting, then the temperature is going to start to increase. And this is a real issue in terms of global warming and climate change. And as our atmosphere is changing because of the different concentration of greenhouse gases, so things like methane and carbon dioxide, that means that it's harder for this extra energy to escape the Earth. So what we're finding at the moment is because the Earth is absorbing more energy than it's emitting, that means its temperature is very slowly rising. So on that bombshell, that is the end of the AQA waves topic. Just a very quick summary. And again, you can find videos that explain all of this in loads more detail at GCSE Physics online. Now, before we start looking at electromagnetism, let's just think about normal magnetism. So this is a bar magnet. It's got a north pole and a south pole. And there's a region surrounding this where a force acts on other magnets or maybe magnetic materials. And we can see that if we put this other magnet over here, something's going to happen, and it's the south end which is attracted to the north. So when you have unlike poles, they attract. If the two poles are the same, they repel. Now for this magnet, the strongest field is going to be at the poles. And we can actually plot this using a small plotting compass, where when you put it on the table, you can see which way it lines up, and then you can actually then start to draw the field lines. But the field lines look a bit like this. So that's just a rough sketch. It's supposed to be symmetrical, and the field lines go from north to south. I'm just going to put some arrows on the diagram to show that. So this is the magnetic field around a simple bar magnet. Now this is also the shape of the magnetic field around the Earth, and this is the reason why if you have a compass, if you're navigating, it always points to north. So the evidence that we have this magnetic iron core in the centre of the Earth is because of the magnetic field that we can experience and actually detect every day. But something really happens if you have a piece of wire and you connect it into a circuit so that there's a current flowing. What we then have is what we call an induced magnet. So just by having a current flowing in a conductor, we then have a magnetic field. Now, if we have a conductor like this, which is just a wire, then if we actually start to look at the field lines, so maybe we've got the current flowing in this direction. I'm just going to draw the field lines in green. What we have are these concentric circles that get more and more widely spaced as we actually draw that. And we can actually think about the direction of this by using our right hand rule. So if this is the direction of the current with my thumb, then my fingers point in the direction that that field is going. So we have the field lines like this. I've just got an arrow to show the direction of that field. Now the thing is, if we had more wires, then we'd have a stronger magnetic field. And actually, if we had it coiled round into a coil like this, we'd have an even stronger magnetic field. Now this coil of wire here, which is a coil of wire that can carry a current, is called a solenoid. And if I was to draw a solenoid a bit like this, I could then draw the magnetic field lines through it. And actually what we find is in the middle we have these lines which are really close together, like this. And they also come around the side like that. In actual fact, this is the same shape as we have around a permanent magnet over here. But in the middle we have this, this dense magnetic field where all the field lines are really close together. Again, these can go from north to south. And so in a solenoid, what this behaves is when you put a current through it, this behaves a bit like a bar magnet. And that's incredibly useful for all sorts of devices. Now when you have a current and it's moving, this then causes there to be a magnetic field. And these three things are really closely linked to one another. So you have a current flowing, so there's a movement of electrons inside a wire, we cause a magnetic field. But what would happen if we had a magnetic field and a current flowed in that? What you then get is the third side of the triangle, you get the movement. And this is called the motor effect. So the motor effect is put to good use in motors. What we have inside this motor here is we have some permanent magnets. When the current starts to flow, we then get movement. And we can actually use something called Fleming's left-hand rule. Now for this, my first finger tells me the direction of the magnetic field. Now a magnetic field we actually give the symbol B to. My second finger tells me the direction of conventional current, and my first finger tells me the direction of the force that a conductor is going to experience, and therefore the direction it moves. So we can see that we've got, from this triangle over here, we've got magnetic field, we've got current, and then my thumb is the force or the direction of that movement. So these three things are really closely linked. Now what this means is that if you had just a single wire in a magnetic field, we could predict which way it's moving. So let's imagine we had the north end and the south end of a magnet like this. Between the two of them there's going to be a region where you have a magnetic field. I'm going to draw this in because we know that the magnetic field goes from north to south. Now this wire here is effectively coming out of the paper towards you. I've just drawn that with a dot. We can then use Fleming's left-hand rule to predict which way that wire would move. So first of all, my first finger is a magnetic field going from north to south like this. My second finger is a current, which is coming out of the paper. It's pretty awkward to do this. And my thumb is pointing up. So what we'd have here is the wire would move in this direction. Obviously we could turn that wire to go downwards by either reversing the direction of the magnets, or we could reverse the direction of that current. So effectively what we're doing there is, if we were to reverse the direction of the magnetic field, this would happen and my thumb would point down. Really awkward to do. If you're in an exam and you see people starting to do this, there's probably a question about the motor effect and Fleming's left-hand rule. But how does a motor work? Well, effectively what you have is you've got a coil of wire, and some of the wire is coming, some of the current flows towards you, some of that current is flowing the other way, and what you then have is, as soon as you pass a current, basically the piece of wire, some of it moves up, some of it moves down, and then you can use a thing called a split ring, and that allows you to then have electric current flowing always in the same direction inside that motor. We can also use an equation to do some calculations, and we can actually look at the size of the force on that conductor. And F is equal to BIL, where we measure our force in newtons, we measure our magnetic field in the Tesla, like the car, current in amps, and length in meters. Now it's not just motors that use the motor effect, we can also use it in loudspeakers. Now in a loudspeaker you might have a very small circular magnet like this, okay, and this is connected to maybe a large paper or cardboard cone. Okay, so you've got your magnet at the bottom. What you then do is you have a coil of wire that comes in and it goes around this several times. Okay, now what happens is that if you have a current flowing in one direction, you've got a current flowing, you've got a magnetic field in this permanent magnet down here, and what that means is that maybe when the current flows this way, the thing here moves up. If you then have the current flowing in the other direction, it moves down. And by varying very quickly which way the current is flowing, that causes the speaker to move up and down, which then causes a load of sound waves to be radiated from this. But this doesn't have to just be a motor. If we think about maybe moving this thing inside a magnetic field, what we're now doing is we are using this as a generator. So by moving this conductor inside a magnetic field, we induce a potential difference, and therefore we induce a current. So a motor and a generator are very, very similar. Again, all we're doing now is completing, I guess, the other side of that triangle. So we can also think about the generator effect. So with the generator effect, if a conductor moves relative to a magnetic field, or the magnetic field around a conductor changes, then we induce a potential difference across the ends of the conductor, and this is, if this is then part of a complete circuit, we then have a current that flows. So how do you make this effect bigger? How do we get more electricity out of our generators? Well, one thing we can do is we can increase the size of the magnetic field. So you make the magnetic field bigger, it's going to cause a bigger voltage. You can also make it move quicker. So V is our velocity here, or speed. So we can move something quicker. And also we can have, if you had maybe a coil of wire which is turning inside the magnetic field, what you can do is you can have more turns. So this solenoid here has one coil of wire, but the amount of times that it goes round gives us a number of turns. So if you have more turns on the generator, that's going to cause there to be a bigger induced potential difference. Now generators, there are really two sorts. We have things which are AC, so alternating current, and this is called an alternator. But you can also have ones which give a DC supply, and this is called a dynamo. And if we were to look at the output voltage with time, what we'd see is for an alternator, you'd get something that looks like this. Now, if you were to spin it quicker or you had a bigger magnetic field, what we'd then have is a higher voltage, but if it's spinning quicker, then we'd have more cycles per second. And the last thing we're going to look at is the transformer. Now, a transformer is really useful in the national grid because what it does is it allows us to change the current and potential difference in a different part of a circuit. Now, what we have here, this is our normal transformer. We have a primary coil and we have a secondary coil. So if this is where the electricity is maybe starting, this is our primary coil. It's got a number of turns and there's a different number of turns on the secondary coil. So what happens is that when you have an alternating current in this wire, this causes there to be an alternating magnetic field, like we saw with the solenoid up here, inside this iron core. So this iron core then becomes magnetized. And what we have is the magnetic field moves this way and then moves that way. What we then have is this iron core transmits that magnetic field to the secondary core. So inside this coil of wire, we then have a changing magnetic field. If you've got a changing magnetic field, which is effectively that magnetic field is moving, we then induce a potential difference. So we then have a potential difference in the secondary coil, which causes a current to flow. So that is the kind of bog standard average transformer that you need to know about for GCSE. So with this, we can think about the potential difference in the primary coil. We can think about the current in the primary coil and also the number of turns on the primary coil. And obviously we can do the same for the secondary. And what we find is that the potential difference increases in proportion to the number of turns from the primary to the secondary. So what we can say is that Vp over Vs is equal to Np over Ns. So imagine that had 5 turns and that had 10 turns. That means you might go from 5 volts to 10 volts. But when you increase that potential difference, we reduce the current. And the other equation we can say is that Vp Ip is equal to Vs Is. So this is effectively power, remembering that power is equal to potential difference times current. If you've got a power coming in, it's the same as the power going out, and that means that the initial power on the primary coil is the same as the power on the secondary coil. Now on a step-up transformer, it steps up the potential difference, so that means there's a bigger number of turns on the secondary coil than the primary. If, however, you had a step-down transformer, you'd have a bigger number of turns on the primary than on the secondary. And what you have in the national grid is that you step up the potential difference when you leave the power station, so it's thousands and thousands of volts, and then you step it back down to eventually 230 volts for use in our homes. So that is a summary of AQA electromagnetism. It can get a little bit tricky at times. If you want to find out more detail about anything in this video, there will be videos at gcsephysicsonline.com. So this is revision of the AQA space physics topic. Now in the universe there are hundreds of millions of galaxies, and the Milky Way is the one that we're in. And in each of these galaxies there are different stars. And what I like to think about is our own solar system, which is surrounding our sun. So you have the sun over here, then we have Mercury, Venus, Earth and Mars. These are the smaller kind of rocky planets, and then further away from the sun we have the gas giants. Jupiter, Saturn, Uranus and Neptune. And to remember the order if you need to, you've got S, U, N, so you start with the sun and you end with the sun. Now in addition to these 8 planets, what we have are a number of moons. So going around the Earth we have our natural satellite, our moon, but don't forget that these other planets as well, they have their own moons as well. So these moons are orbiting their planet, and we do have some other things which are orbiting the sun. For example, you've got comets, which maybe aren't round, but we have these kind of comets and asteroids, and maybe these have a more elliptical orbit around the sun. But where did our sun come from? Well, it started out in a nebula. Now, a nebula is just a massive cloud of dust and gas. And all of these particles, they're all attracted to one another due to the force of gravity. And what they do is when they come together, they lose some of their potential energy, and that's transferred to their kinetic energy store. And this then forms what we call a protostar. And eventually this protostar turns into what we call a main sequence star. And this is basically where the star is in its stable phase. It's going to spend about 95% of its life there. And basically what you have is there's an equilibrium between the fact that gravity is pulling everything in, and there's nuclear fusion happening, which is kind of pushing everything apart. And this is where the star's in equilibrium. It's not getting bigger or smaller. So that's the main sequence. And if we have a star a bit like our sun, so a sort of low to medium mass star, that's where it's going to spend most of its life. But at the end of its life, it starts to run out of fuel, the hydrogen that it's fusing into helium. And what happens then is it actually expands, it gets cooler, but it gets bigger. And then it becomes a red giant. Now, when it's a red giant, we're having fusion of heavier elements, but it gets to a point where it just runs out of fuel. And at that point, it then gets smaller and smaller and shrinks. Now, as it shrinks, the surface does get hotter. And this is basically where it kind of dies effectively, and it's very, very small, so it's called a dwarf. And because it's got the actual surface has got hotter, even though it's giving out less energy, this is what we call a white dwarf. And eventually, after billions and billions of years, this white dwarf is going to cool down to make a black dwarf. So this is the stellar evolution, what happens to a star like our sun through its lifetime. But we also have bigger stars as well. So again, if you have a bigger star, it's going to start in a dust cloud called a nebula. But this time, because there's more stuff that comes together, what we get is a bigger protostar. And a bigger protostar is going to make an even bigger main sequence star. Now this main sequence star, because it's bigger, there's more stuff, so there's a bigger force due to gravity pulling everything in. And that means that actually bigger stars burn through their fuel a lot quicker. They often burn brighter, so this is more of a whitey to even blue colour compared to the yellowy orangey colour of stars like our sun. So this main sequence star, it burns through its fuel really quickly, so it gets to the red giant stage really quickly as well. And then it becomes a red supergiant. And again, this is furiously burning fuel, and at the end of it, what happens is there's no more fuel, the force of gravity pulls everything in, and the outer parts of that star bounce off the very dense core that's remaining. And then there's this massive explosion, which, basically lights up a whole galaxy. This is called a supernova, and then one of two things can occur. Basically, whatever's left over, the core that's left, it's basically giving out a huge amount of energy, and it's spinning really quickly. And effectively, all of the particles inside, because there's no fusion taking place, all of the electrons and protons have been pushed into each other to make neutrons, and it's a bit like a massive nucleus for an atom. So this one here is what we call a neutron star. But if the star is super big, then actually everything would just keep collapsing under gravity. There's no force that can actually cause this to not get any smaller. And what happens then is that all of this mass ends up shrinking into effectively no volume. Pretty weird stuff, but this is called a black hole. And these are absolutely fascinating. The strength of gravity is so much that not even light can escape. Now, we can't really actually directly see a black hole necessarily. We can maybe only see the effects that it has on things nearby. But there's no light being emitted, so we can't actually see light shining out of a black hole. Now, gravity is super important. Gravity is what's pulling everything together, so things heat up, and that allows fusion to take place. So fusion is a joining together of light nuclei, and this means that we start to create new elements. Although anything that's bigger than iron, because iron is the most stable element, anything which is bigger than iron, maybe the iron in your body at the moment, maybe any gold you have in your jewellery, that must have been created in a supernova. Now, when the supernova happens, it kind of distributes these elements throughout the universe, which then might end up making another nebula, and then that then forms maybe the star in the centre of a solar system, as well as the material for the planets. So you've been formed in one of these supernovas. Now, the other thing that gravity does is it allows all of these planets and all of the satellites to remain in orbit. Because if you have maybe a sun here in the middle, and you've got the Earth which is orbiting around it at a certain speed, there's a force of gravity that's pulling this in. And what this gravity is doing, it's a force that isn't changing the speed, but it's changing the direction. And this then means that things follow a circular path. That's supposed to be a circle there. But you can have things like this comet over here. Now this can still have a stable kind of elliptical orbit around maybe a sun over here. But what happens here is that as it gets closer, because it's losing some of its potential energy that's been converted to the kinetic store, it moves slowly a long way away, then it travels really quickly as it goes near the sun, sort of slingshotted round, and then its velocity decreases again. So we can still have a stable elliptical orbit for objects like comets, but this is where they're travelling slowly a long way away from the star, and they travel a lot quicker when they get closer to it. Now we've seen that stars have a lifetime, and actually what we find is that when we look at stars which are a long, long way away, we seem to see that actually some of the light that they emit seems to be stretched, and actually the universe is expanding. Now if it's expanding now, that meant yesterday it was a little bit smaller and the day before it was a bit smaller, and if we go far back enough in time we find that actually there was a point when the whole universe had no dimensions, and this is the point that we call the Big Bang. Now the Big Bang happened about 13.8 billion years ago, and at that point all of space and all of time was created. It's very strange to think, but before the Big Bang time didn't exist. So this started everything. So the evidence for the Big Bang is that when we look at light from stars, maybe this is what the light should be. When we look at light from distant stars, that light all appears to be stretched. Now the wavelength has increased, and if you remember from your work on the electromagnetic spectrum, when you have a longer wavelength, we then have red light. So what we see is that things which are further away, there's something that we call redshift. And actually, when we look at different galaxies which are even further away the galaxy is, the bigger the redshift of that light. And that means that everything is expanding away from everything else in the universe, which meant at some point it must have all been in the same place. And there's some kind of clever physics we can do to actually work out that this is 13.8 billion years old. Now in the last 20 years or so we found that not only is the universe expanding, but the rate of expansion is getting faster and faster and faster. So we don't quite know exactly why that is, and that's the really interesting thing about science. You know, we don't know all of the answers. Obviously telescopes are getting better, we've got more people working on it, we've got things like LIGO looking at gravitational waves, super exciting bits of physics. And it might be that there's dark matter or there's dark energy which is driving this rapid inflation of the universe. But basically, this is just a quick bit of revision of a small amount of space physics, a super fascinating topic. So we've got the parts of the solar system, we've got evolution of low mass and high mass stars, as well as evidence for things like the Big Bang. So this is a summary of the AQA required practicals. Now the ones in blue are if you're doing the GCSE Physics only, but the ones which are just in white are the ones for the combined award. Now the thing is, depending on what equipment you might have at your school, you might be doing these in different ways, and when it comes to the exam they might ask you about some of these methods, or they might be using this equipment that you've used before, maybe in a slightly different way. So let's begin by looking at specific heat capacity. So this is the equation linking the change in thermal energy with the mass of something, the specific heat capacity and its change in temperature. Now, in order to find the specific heat capacity, again, there's different ways of doing this, but that means we need to know the energy supplied to something, we need to know how heavy it is, and we also need to look at its change in temperature. Now, if you're looking at a solid, you might have one of these blocks here. So what you do is you'd have this electric heater, and what you do with this is you would measure things like the current and also the potential difference. Now, the power transferred is going to be equal to the potential difference times the current, and then to work out the total energy you're going to be multiplying the power by the time. So the energy transferred is equal to the power times the time. Another way you might be doing it is you might be having a liquid. So here you'd have maybe a beaker, again you'd have this metal heater inside it and your thermometer, and around this you'd make sure that there's plenty of insulation and a lid on top to reduce any heat losses. And again, what you're doing is you're just heating up this thing. So there's different ways you can interpret your data. It might be that you plot a graph. Now if you plot a graph like this, you've got your temperature change up the side and the energy transferred here. You can then work out the gradient of this part of the line. And what you can then do is find that your specific heat capacity is 1 divided by the mass times the gradient. Depending on which equipment you use at school, effectively you've got a known mass of either a solid or a liquid. You're heating it up, and when you heat it up, you need to measure the current, the potential difference, and the time in order to work out the energy transferred. You can then plot a graph, and then you work out your specific heat capacity from 1 over mass times the gradient. Now, investigating the effectiveness of different materials as thermal insulators, there's different ways to do this. A simple way is you'd have a beaker. Perhaps inside this beaker you've got some water, and then you have your thermometer. So in this investigation, what you can do is you can look at the rate of energy transfer by maybe recording the temperature at different times. You could then repeat it using different amounts of insulation or different materials that surround it, remembering that you keep certain things the same. So you might, for example, use a cardboard lid each time to reduce any evaporation and heat loss from the top, and then you're just really looking at the different materials and how these help as an insulator. So this one here, pretty straightforward to do, and then you can maybe plot your data with a graph, or it might be a bar chart if you're looking at different types of material. For this one here, when you set up circuits to look at the length of wire, what you need is some kind of power supply, maybe a cell or a battery. You have an ammeter that you connect in series, and then you'd have your sample of wire. So this is a piece of wire, and you can measure the length of that wire. You also have a voltmeter that goes in parallel across it. Now, the reason for this is that if you know the current and the potential difference, you can work out resistance, where resistance is equal to the potential difference divided by the current. You'd also have a varying length of wire here, so you've got a different length of wire each time. And what you should see then is that as you have a bigger length of wire, you should find, hopefully, that the resistance increases. You double the length of wire, you double the resistance. Something else you can also look at is resistors in series and parallel. And for this, you'd do exactly the same. You'd have your ammeter, your voltmeter, and rather than having a piece of wire here, what you'd have instead would be a combination of resistors. And you'd make sure that the voltmeter went across both of these. Now, what you should find is that as you have more resistors in series, the total resistance goes up. But if you had resistors in parallel, then the total resistance should decrease. Next, we need to look at circuits to investigate the IV characteristics of resistors, lamps, and diodes. Again, it's a very similar circuit to the one that we have over here. You're still measuring the current, and you're going to be measuring the potential difference. But what we can do is we can use a variable resistor, and this then allows us to change the current and potential difference across the component. Now, in this point here I've put an X, that's where you put your component. Now, you then take values when you've got a positive value of current and a positive value of potential difference, and then you just need to swap the cell around so it faces the other direction to get values which are negative. You should find that when you plot these on a graph, so you've got I and V, you should find that a resistor is a straight line that goes through the origin. When you have a filament lamp, it does something like this, and that's because the resistance changes. A diode is tricky to do, especially when the current is going the other direction, but when you look at the IV characteristics for this, it should be negative, or it should be 0 when the potential difference is one way, and then it rises steeply like that. But this one here is difficult to get the readings from. Next, we're looking at density, and the density is equal to the mass divided by the volume. Now, in all cases, you can find out the mass using a mass balance, and that should then give you your mass in kilograms or grams. To work out the volume, it's a bit more tricky. Now, for a regular object, it might be a cube. You can work out the volume by using a ruler or some calipers or a micrometer, and then the volume of a cubic shape like this is just going to be equal to length times width times height. And the same if you had another regular object like a cube, it would just be length times length times length. Irregular objects are a bit more tricky because here you can't just measure the dimensions. Instead, what you can do is use a Eureka can, and then you also have a measuring cylinder. And when you put the object and you completely submerge it under the liquid, you've then got your object in here, and this displaces an equal volume of water. And if you have a liquid, this is actually pretty straightforward. You just have that liquid in a measuring cylinder, and then if this liquid's in the measuring cylinder, you can just read off the volume directly. Remembering, of course, that 1 milliliter is the same as 1 cubic centimetre. Next we're going to look at the relationship between force and extension for a spring. So for this you need some kind of retort stand, and at the top of this you hang your spring and you measure the initial length. You then add masses onto the bottom, or you add weights onto the bottom, and this causes the spring to get longer. And what you're then measuring, if that's the initial length of the spring, is we're measuring the extension, so how much longer it's got. And you also should remember that 100 gram mass is approximately 1 Newton. You should also find that provided you don't go beyond the elastic limit, when you look at the force that's being applied to that spring and the extension, you get this linear relationship. And what we find is that the gradient here is equal to the spring stiffness. So K is equal to our force divided by extension, and you find that by looking at the gradient of the line. Investigating the effect of acceleration of the force on a constant mass, a standard way of doing this is you have your lab bench, and at the end of this you have a pulley. And what you then have is one of these physics trolleys connected with a piece of string. It goes over the pulley, and then you have a mass down here, a weight, which is providing the force which causes this to get quicker. Now for the first one, you vary the force by adding different masses on here, but we need to keep a constant mass, and the key thing is that the total mass of the truck and the weight, because it's all accelerating, has to stay the same. So the way that you do this is you'd have some masses on top, and what you do is you take the mass from the top and you put it onto here, and that means your total mass of the thing stays the same, but you're changing the force, because that means the force which is pulling down, the weight acting down, is going to be bigger each time. If you vary the mass for a constant force, that means you just keep the same thing on here, and you maybe just add masses to the trolley on the top. Does that make sense? There's kind of a subtle difference between the two. For the first one, you keep the tote, you're just changing mass from here to here. For the second one, you're just adding mass to this, and that stays the same. You then have some kind of data logger. Depending what your school has used, there might be a force sensor or an accelerometer which gives you a reading of the acceleration directly. It might be that you're using light gates, or you're timing it to work out the speed to then work out the acceleration, which is what you're trying to measure. What you should find is for the same mass but an increasing force, the acceleration gets bigger. But when you have the same force but you're varying the mass, as you get something bigger, the acceleration goes down. So you get a graph that looks a bit like this. The next one is looking at the frequency, wavelength and speed of waves in a ripple tank and waves in a solid. So the ripple tank, this is kind of a top-down view of it, and you might have a kind of dibber or something that goes up and down, and what you can then is you can read the frequency of that off the signal generator. So that gives you your frequency. You can then measure the wavelength either by using your phone, for example, which would then give you a slow-mo image which you could then pause, and you can then measure the wavelength, especially if you have a grid by the side that shows this. Sometimes you can also use a strobe light, and if you get that just right and it matches the frequency, we then effectively freeze the image of the waves, and you can then measure that using a ruler. For waves in a solid, the way that we tend to do this is, again, we have a signal generator connected up to a vibration generator. This is then connected to a string that goes over the edge of a bench. And if you get this just right, what we do is we set up lovely standing waves in the string. So what you see is that string kind of starts to oscillate wildly. You can then read off the frequency off your signal generator. You can measure the wavelength using a ruler, and then you can use that to then work out how quickly that wave is moving. To look at the reflection of light, we can have a mirror that we set up. We then use a ray box, and we can shine a ray of light at that mirror. You then draw in a normal at 90 degrees to the surface, and then you can mark out where that reflected ray goes. Perhaps you see a ray that comes out here, you draw a couple of crosses, and you join up the dots with your ruler. You can then measure the angle of incidence and the angle of reflection. You can do something similar when it comes to looking at refraction. So maybe this is a glass block, and once again you shine a ray of light at it, you draw in your normal line, and then you just put a couple of crosses or maybe a point where that ray of light comes out. You can then join it up using a ruler, and then once again you can measure the angle of incidence and the angle of refraction. You should find that for reflection, I is equal to R, but for refraction, you should find that I, if it's something maybe going into glass, the light slows down, and I is bigger than R, the angle of refraction. And this one here, looking at infrared radiation, this is where we're often thinking about things which are matte black, which are brilliant absorbers and emitters, or shiny silver, which is a poor emitter and poor absorber. So one way you could do this is you could set up two beakers. One of them is silver, one is matte black. In each of these you could have your thermometer, and then you have some liquid in both. And you can also have a lid along the top to stop any heat leaving that way. Now you'd make sure that one is silver and one is black, or you can change different colours to investigate it. What you can then look at is how quickly that temperature drops. Effectively, the greater the temperature drop, the greater the amount of infrared radiation being emitted. So you can look at that for silver and black. The other way you can do it is if you had maybe a heat source and then you had two of these thermometers, or you can even use data loggers to actually record it digitally rather than have to take manual readings. You could look at how maybe a silver-coated thermometer changes its temperature compared to a matte black painted thermometer if they're both the same away from a heat source. So that's investigating how much that infrared radiation is absorbed by the thermometer. So that is just a really quick summary of the AQA practicals. You will have done these at school, you might have used different methods. Something that's important to do when it comes to looking at exam questions is maybe thinking about your independent variable, the one that you decided to change, how that affected your dependent variable, and then also the control variables that you kept the same each time to make sure it's a fair test. Again, when it comes to your method, you've got to think about the equipment that you use, so label it very clearly, and diagrams do help. Think about the measurements that you take and how you had accurate measurements. And also think about any safety considerations. For example, things get hot if you're looking at specific heat capacity. You've got electric currents here, which can potentially be a bit dangerous. You've got liquids which might spill and cause a kind of a trip hazard. You've got masses and weights which might fall on the ground and cause somebody an injury. So there are no big risks. I mean, it's pretty safe doing GCSE physics, but you've always got to make sure that you think about any of the hazards and then how you control these if you're doing the experiment. So those are the AQA required practicals.